Okay, I'm back. And the question you should ask yourself is, what is it that this permutation matrix does? Well, it swaps the first row with the second row. So, you would think that in order to undo that, you need to again swap the first row with the second row. And therefore you would conjecture that this would be the inverse of that permutation matrix. Indeed, if you multiply these two matrices together, you get the identity. So what about this one? Now, you may have thought that what's going on here is that the inverse of any permutation matrix is that permutation itself, because this matrix is just that matrix. That turns out not to be the case. So here's another permutation matrix. Now what's happening here? We get that the row indexed with 2 becomes the row indexed with 0. The row indexed with 0 becomes the row indexed with 1. And the row indexed with 1 becomes the row indexed with 2. So notice that that's like rotating the elements of a vector to which you apply this by 1. And we're rotating down in this case. Okay, so how do you undo that? You rotate up by 1. What is the matrix that rotates up by 1? Let's see. This element needs to go up 1, so it's the matrix where you put a 1 here. You put a, let's see here, a 1 here, and a 1 there. And if you multiply these two matrices together, you get the identity matrix. Now this here is the transpose of this permutation matrix. If this was P. So maybe it's the case that the inverse of a permutation is the transpose of a permutation. Does that work here? Well, here that would work, right? Because this matrix is not only that matrix itself, what we actually have here is a symmetric matrix. That was the next question that you were asked. Is it the case that P inverse is equal to P? And we just saw an example where that's not the case. But we also saw an example where it is the case, so it turns out to be sometimes. Is it the case that P inverse is equal to P transpose? Well, I'm going to guess always. And the way I'm going to justify this is going to be a little complex, but I spend a lot of time thinking about this, so I'm going to make you suffer through my explanation. Okay, this gets a little involved. Let's let this be the permutation vector such that the permutation that we're talking about is just the permutation that has the action of reshuffling the components of a vector in the indicated order in this vector. What does that mean? That means that when you apply P to a vector x, you reshuffle that vector in the order that is given here. Now what we would like to do is undo this. So we want some kind of matrix B that is going to turn out to be the inverse of that matrix P. And here I'm also showing B as the columns. Okay, now notice that I've multiplied both sides by B, so I have not changed the equality there. What we would like to come out of this is the original components in the original order, 0, 1, 2, 3, etc. Okay? So we don't know what B is, but we do know that we want the action of B on this vector right here, which was the shuffled vector. We want the action of that matrix B to be that it puts everything back in the right order. Now, we remember from when we introduced vectors and unit basis vectors that we can think of any vector as just the linear combination of the unit basis vectors. And that's what we have expressed here. On the right, we have learned that performing a matrix vector multiplication is the same as taking the linear combinations of the columns of the matrix, where the coefficients for the linear combination are given by the components of the vectors. Now, we can reshuffle all of these terms because vector addition is commutative. And we're going to reshuffle them so that the coefficients here end up in the exact same order as the coefficients on the right. Okay. Now notice that because those coefficients still multiply the exact same unit basis vectors, this right here is the same as this linear combination. But now we can take a pretty good guess at what our columns of matrix B must be. Okay? They must be the unit basis vectors. Oops. This should have been k sub 1, not k minus 1. They should be the unit basis vectors, but ordered in the exact order given right here. So then we guess that P inverse is just this matrix B, which is just the unit basis vectors ordered in exactly the order indicated by the permutation vector. Notice that that's the same as the transpose of those unit basis vectors written as rows. And then this we recognize as our matrix P, and therefore we conclude that the inverse of a permutation matrix is simply its transpose. Now, we could have saved ourselves a lot of grief if we simply had guessed at that and multiplied things out. So to check whether P inverse is P transpose, we just look at P times P transpose, which is just P identified by its rows as such. Transposing that means that you get the rows that are the unit basis vectors times the columns that are the unit basis vectors in this order. And if you multiply all of that out, then you get all of this, and you recognize that the elements on the diagonal are all equal to 1, and all of the elements on the off diagonal are equal to 0, because the inner product of two unit basis vectors that are not the same unit basis vector is 0. And therefore we get the identity. Okay, let's move on to the next homework exercise. Remember how a rotation rotates a vector through an angle theta. Here's a picture of it. Remember that the matrix that represents that rotation is given with cosines and sines of the vector theta. And what we now want you to do is to go and think about what transformation will undo this rotation and what the matrix is associated with this. So go ahead and do that homework.